Hi students, in today's class we will study the symmetrical component transformation of a three-phase system. We consider this three-phase transmission system supplying a motor load. Suppose the currents through the three lines are IA, IB and IC. In the normal condition, these three currents will be balanced. So this can be represented using three vectors. This is IA, this is IB, this is IC. These three vectors are balanced because they have equal magnitudes and the angle between any two vectors is 120 degrees. Suppose they are rotating in the anti-clockwise direction. The phase sequence of these vectors is A is the reference vector, B follows A, C follows B. So A, B, C. This is the phase sequence of these three vectors. It is a sequence in which the vectors are rotating. Now, suppose a fault occurs in this particular transmission system. So one of the transmission lines breaks and falls on the ground. Now the three currents IA, IB and IC are no more balanced. They become unbalanced. At this particular condition, suppose these are the three vectors. This is IA, this is IB, and this is IC. These three vectors are rotating in the anti-clockwise direction. Here the phase sequence is A, B, C. Now the symmetrical component transformation says that these three unbalanced vectors can be formed using three sets of balanced vectors. This is the first set of balanced vectors. IA1, this is IB1, this is IC1. They also rotate in the same direction as the original unbalanced vectors. Here the phase sequence is A, B, C. This vectors also has the same phase sequence A, B, C. So we call this vectors as positive sequence vectors. Which has the same phase sequence as the original vector, original unbalanced vector. Let me draw the second set of balanced vectors. This is IA2, this is IB2, this is IC2. Here the phase sequence is A, C, B. They also rotate in the same direction as the original vectors. But the phase sequence is opposite to the original unbalanced vectors. So we call it negative sequence vectors. And the third set of balanced vectors, this is IA0, This is IB0. This is IC0. They all are in the same direction. We call it zero sequence vectors. So any unbalanced vectors can be formed by adding positive sequence vector, negative sequence vector and zero sequence vectors. So positive sequence vectors have the same phase sequence as the original unbalanced vectors. Negative sequence vectors have the phase sequence opposite to the original unbalanced vectors, and the zero sequence vectors, they all are in the same direction. Now we will check whether we can form this unbalanced vectors by adding these three sequence vectors. We'll consider one particular case. Suppose this is the positive sequence vector, IA1. This is IB1. This is IC1. Let's add all the sequence vectors for the A phase. This is IA1. This is your IA2. This is IA0. This is the resultant vector IA. This is IA. It is not to the scale. This is our IA. We will add all the sequence components for the B phase. This is IB1. This is IB2. And this is IB0. Let's find out the resultant. This is IB. This is our IB. Now let's add all the sequence components for the third phase. This is IC1. This is IC2. This is IC0. Let's find out the resultant. This is IC. This is the third component of our unbalanced vectors. So we understood that if we add positive sequence, negative sequence and the zero sequence vectors, we will get the unbalanced vectors. And consider the complex xy plane. We consider a magnitude of 2 both in the x-axis and in the y-axis. This is how we write the magnitudes. X is equal to 2 and y is equal to j2. This is our j-axis, where this operator j equals one angle 90 degrees, because the y-axis leads the x-axis by 90 degrees. That is represented by the operator j. Here IA1 is the reference vector. IC1 leads IA1 by an angle of 120 degrees. This is represented by the operator alpha. Alpha equals one angle 120 degrees. So IC1 equals IA1 into alpha. This alpha into IA1. Here this y equals j into 2. Here the j stands for y-axis leads the x-axis by an angle 90 degrees. Here this alpha stands for one angle 120 degrees. So IC1 leads IA1 by an angle 120 degrees. So IC1 equals alpha into IA1. IB1 equals alpha into IA1 because IB1 leads IA1 by 240 degrees. So it is alpha square into IA1. Here IA2 is the reference vector. IB2 leads IA2 by 120 degrees. So it is alpha into IA2. IC2 equals alpha into IA2 because it leads IA2 by 240 degrees. When it comes to the zero sequence vectors, all are equal. IA0 equals, IB0 equals, IC0. Let me write a couple of properties of this alpha. 1 plus alpha square is equal to 0. Then alpha cube is 1. Alpha equals 1 angle 120 degrees. Alpha cube is 1 angle 120 into 1 angle 120 into 1 angle 120, which is equal to 1 angle 360 degrees, which is equal to 1. Alpha raised to 4 equals alpha cube into alpha, which is equal to alpha because alpha cube is 1. These are the properties of the operator alpha. Now IA equals the unbalanced vectors can be represented as sum of positive sequence, negative sequence and zero sequence vectors. So IA equals IA0 plus IA1 plus IA2. The second phase current IB equals the zero sequence current plus positive sequence current plus its negative sequence current. IB0 is same as IA0. IB1 equals alpha square into IA1 plus IB2 equals alpha into IA2. So this is our IB. And IC equals zero sequence current plus positive sequence current plus negative sequence current. IC0 is same as IA0 plus IC1 equals alpha into IA1 plus IC2 equals alpha square into IA2. So these are the three equations in terms of positive sequence, zero sequence and a negative sequence. So these are the phase currents in terms of sequence currents. Let us write these three equations in the matrix form. IA, IB and IC. This is equal to IA0, IA1, IA2. IA equals IA0 plus IA1 plus IA2. So the coefficients are 1, 1 and 1. IA equals IA0 plus IA1 plus IA2. IB equals IA0 plus alpha square into IA1 plus alpha into IA2. The third phase current is IA0 plus alpha into IA1 plus alpha square into IA2. So using this equation, we can find out the phase quantities if the sequence components are given. Now we will write equations to find out the sequence components from phase components. Now we have to find out IA0, IA1 and IA2. When IA, IB, IC are given, these are the phase currents. When phase currents are given, how we can find out the sequence current? Using this equation, we can find out the phase currents if sequence currents are given. Now we are going to find out some expressions to find out the sequence currents from phase currents. Now if we add these three equations, on the left hand side we will get IA plus IB plus IC. So this is 3IA0. So this is IA1, this is alpha square into IA1, this is alpha into IA1. So it becomes 1 plus alpha square into IA1. As you know, 1 plus alpha square is equal to 0. So this term getting cancelled. Here this is 1 plus alpha square into IA2 getting cancelled. Plus 0 plus 0. So IA0 equals 1 by 3 into IA plus IB plus IC. So it's IA plus IB plus IC. So IA0 equals 1 by 3 into IA plus IB plus IC. IA0 equals 1 by 3 IA plus IB plus IC. Now we multiply the second equation with alpha and the third equation with alpha square. Now on the left hand side we will be getting IA plus alpha IB plus alpha square IC. This is equal to 3. So this is alpha into IA0. This is alpha square into IA0. So here IA0, alpha IA0, alpha square IA0. These three will be getting cancelled. 1 plus alpha square equals 0. So this becomes 1 plus alpha square into alpha. This is equal to alpha cube, which is equal to 1. And the last term it becomes alpha square into alpha cube. This is 1. So IA1 plus IA1 plus IA1. It becomes 3IA1. The last term, this is IA2. When it is multiplied by alpha, it becomes alpha square IA2. It becomes alpha raised to 4 into IA2. Alpha raised to 4 is same as alpha. So alpha IA2, alpha square IA2, IA2. So this is IA2 into 1 plus alpha square will be getting cancelled. So what is IA1? 1 by 3 into IA plus. IA1 equals 1 by 3 into IA plus alpha into IB plus alpha square into IC. So using this equation we can find out IA1. Now to find out IA2, we multiply the second equation with alpha square and the third with alpha. On the left hand side, IA plus alpha square IB plus alpha IC. This is IA0, it becomes alpha square IA0, it becomes alpha IA0. So this becomes IA0 into 1 plus alpha square becomes 0. Here it is IA1, this is multiplied by alpha square. It becomes alpha raised to 4 into IA1. That is alpha into IA1. It becomes alpha square into IA1. So here also, the second set of terms getting cancelled as 1 plus alpha square is 0. Then the last term, it is multiplied by alpha square. Alpha square into alpha equals alpha cube. This is 1 into IA2. And the last term, it is multiplied by alpha. Alpha into alpha square is alpha cube. This is 1. So it is IA2 plus IA2 plus IA2. It's 3 IA2. So IA2 equals 1 by 3 into IA plus alpha square into IB, alpha square into IB plus alpha into IC. So using this expression, using this equation, using this matrix equation, we can find out the sequence components if the phase components are given. So when sequence currents are given, we can find out the phase currents. When phase currents are given, we can find out the sequence currents. So the symmetrical component transformation says that if we have any set of unbalanced vectors that can be formed using 3 sets of balanced vectors. One is positive sequence, the other is negative sequence, and the third set is zero sequence. Using these 2 equations, we can find out the phase quantities if sequence quantities are given. Using this equation, we can find out the sequence quantities if phase quantities are given.